Hello, my rubber hearts. Welcome back to another episode where we explore the incredible world of rubber and polymers. Today, we're diving into the geometric configuration of polymer chains, a topic that plays a huge role in determining the properties of the elastic material we use every day. In this episode, I'm going to break down what polymer chains are, the different geometric configurations that are possible, and how these configurations affect the properties of synthetic rubbers. Whether you're a rubber industry professional or just curious about how your favorite rubber products work, this episode is for you. Let's jump in. Before we get into the geometric configurations, let's quickly talk about what a polymer backbone is. Imagine a polymer as a chain made up of smaller repeating units called monomers. The backbone is the main part of the chain, made up of atoms, usually carbon atoms, bonded together in a long continuous line. The way this backbone twists, bends, or arranges itself is what we call the geometric configuration of the polymer. In other words, it's the shape that the polymer takes. This shape is crucial because it affects how the polymer behaves, whether it is stretchy, rigid, or sometimes something in between. Now, there are different ways these polymer chains can arrange themselves. Let's talk about the main geometric configurations. We have configurations like cis and trans, and then syndiotactic, isotactic, and atactic configuration. These configurations may sound technical, but don't worry. I'm going to explain each one in an easy to understand way, and we will look at how they affect the properties of synthetic rubber. Let's start with the cis configuration. In this setup, the side groups attached to the polymer backbone, usually hydrogen atoms or larger groups, are positioned on the same side of the chain. In rubbery materials like natural rubber, the polymer chains typically adopt a cis configuration. This gives the polymer a kinked structure, meaning that the chain can bend and twist easily. Because of this flexibility, cis-configured polymers are highly elastic. That is why natural rubber can stretch and return to its original shape so well. It's all thanks to the cis configuration. The cis configuration is also what gives rubber its bounciness and stretchiness, which is why it's used in products like tires, elastic bands, and inflatable materials. Next, we have the trans configuration. In this case, the side groups are positioned on opposite sides of the polymer backbone. This makes the polymer chains more linear and rigid compared to the cis configuration. Trans-polyisoprene, for example, is found in a material called gutta-percha, which is a naturally occurring rubber. Unlike natural rubber, which is soft and elastic, trans-polyisoprene is much more rigid and brittle. The trans configuration forces the chains to line up closely, creating a more crystalline structure, which results in a harder material. Polymers with trans configurations are used in applications where stiffness is needed, like in golf balls or certain types of hard rubber products. Now, let's move on to something a bit different. Syndiotactic configuration. This refers to the arrangement of the side groups along the polymer backbone in an alternating pattern. One side group is on the right, the next is on the left, and so on. This regular alternating pattern helps the polymer chains pack together tightly, making the material more crystalline and rigid. Syndiotactic polymers often have higher melting points and are more heat resistant than other configurations. Syndiotactic polymers, like syndiotactic polystyrene, are used in high performance applications where strength and heat resistance are important. In the rubber industry, syndiotactic configurations are less common, but they can be useful in creating harder rubber materials. The isotactic configuration is another common geometric arrangement. In this case, all the side groups are positioned on the same side of the polymer backbone. This uniform arrangement allows the polymer chains to pack together very efficiently, creating a highly ordered and crystalline structure. Isotactic polypropylene is a great example of a polymer with an isotactic configuration. While not as flexible as natural rubber, isotactic polymers are known for their strength and durability. In the rubber industry, isotactic configurations are used when a tough, resilient material is required. Isotactic polymers are often found in products like bumpers, plastic containers, and certain types of synthetic rubbers. And last but not least, we have the atactic configuration. In an atactic polymer, the side groups are arranged randomly along the polymer backbone with no specific pattern. This randomness prevents the polymer chain from packing together tightly, making the material amorphous, meaning it doesn't form a crystal-like structure. Atactic polymers are generally softer and more flexible than their isotactic or syntactic counterparts. Because the chains can't line up in a regular way, the polymer tends to be more rubbery and less rigid. An example is atactic polystyrene, which is used in packaging and foam products. Atactic configurations give polymers more flexibility and softness, making them ideal for rubber products that need to be more malleable, like gaskets or seals. Now that we have covered the main types of configurations, let's focus on which ones are most common in synthetic rubbers used in everyday products. Cis configuration. As we mentioned earlier, the cis configuration is the most important for materials like natural rubber and butadiene rubber, which is used in tires. This configuration gives rubber its elasticity, making it perfect for products that need to stretch and rebound. The trans configuration, while less common than cis, is crucial for products that need more rigidity like golf balls or certain hard rubber products. Many synthetic rubbers like styrene-butadiene have atactic configurations, which make them flexible and suitable for things like tires, footwear, and soft touch items. Lastly, isotactic and syntactic configurations are less common in the rubber industry, but are essential for creating tougher, more heat-resistant materials. For example, isotactic polymers are used when synthetic rubber needs to be stronger, such as in automotive parts or industrial applications. So, how do these configurations come to be in the first place? It all depends on how the polymer chains are synthesized. The type of catalyst and the conditions under which the polymerization occurs plays a huge role in determining the final configuration. For instance, certain catalysts can control whether the polymer forms a cis or trans configurations, while others influence whether the chain is isotactic, syntactic, or atactic. These factors are carefully controlled in the production of synthetic rubbers to give them the exact properties needed for their intended applications. So there you have it. The geometric configuration of polymer chains might sound complicated at first, but it's all about how the side groups and the backbone arrange themselves. This arrangement plays a massive role in how rubber behaves, whether it is bouncy and flexible or hard and rigid. If you enjoyed learning about polymer configurations and how they affect the world of rubber, don't forget to like and subscribe to the channel for more deep dives into the science of rubber. Let me know in the comments what other topics you love to learn about. Stay bouncy, and I will see you in the next episode.